Hello everyone, my name is Abdullah Al Hassan and we're having the Project 1 presentation. So we have choose the strip problem to solve it. So our problem is we have a long thin strip of a charge that is in the xy plane. The strip is infinitely long in the x direction but has a width of 2L in y direction. The strip center is at the origin and the charge density sigma changes with respect to y coordinates given by sigma y equals sigma naught y, times y over L. Alright, so over here we have all our formulas that we're going to be using, starting with Coulomb's law, and we've chosen Coulomb's law to describe the electric field produced by a point charge dq at a distance r. Then we have the electric potential due to continuous charge distribution, and we have chosen this one because this formula calculates the electric potential V at a point due to a continuous charge distribution by integrating the electric field E along the path dl. Then we're using the linear charge density, which is y naught of y equals the y naught y over L, and this formula describes the linear charge density sigma y as a function of position along the y-axis. Then we have the charge elements, which are dq equals to sigma y of y prime dy prime. And this formula calculates the infinite small charge of element dq. Then here we have our assumptions, where the first one is the strip is infinitely long on the x-axis, and the charge density varies only with respect to y coordinates. We use Coulomb's law to calculate the electric field, and it's a scalar field, so we can integrate to find the electric potential, assuming V equals 0 where y equals 2. So here is our diagram that we have based on our assumptions, where we have when V equals 0 we have a y equals 2L, and here's what it shows our diagram. So basically from the origin down there it gives us a 1L, and from the origin up there is a 1L. Combined together will give us the 2L as we have in the problem.
Hey everyone, my name is Jesse Noden, and I'm going to do the problem solving aspect of the problem. So let's start. Right here, just our equations that we're going to use. We got the charge density, the linear charge density right here, which is sigma naught over L times y dy, and that's our lambda, and that's going to come into play for our dE, which we're going to integrate, but to get rid of the d. But we notice this r at the bottom, and we know that we need to minus the total distance above the strip minus the y. So we plug r in for this, right? And so to isolate this whole part, after we plugged in lambda, our charge density, we integrate both sides, and our bounds, negative L to L, that is the entire strip. So we have 2k times sigma naught over L times y over d minus y, and that's dy in the y hat direction. We're going to integrate up because we want to find everything above the strip. So we plugged that into Wolfram, and it gave us this equation right here. So our electric field is 2k sigma naught over L times d natural log of d plus L over d minus L minus 2L, where d is greater than L. So now that we found the electric field, we need to find the electrical potential. And so we're going to use this equation and plug it in for our V equals equation. So V equals negative indefinite integral of electric field times dl. So we're going to plug this E into this E right here, and this is what we get right here. So plug it in, and you might notice that we changed the dl to dd, and that's because we want to integrate everything above the d. So that's the distance in the y hat direction. And so we plug that into Wolfram, complicated integral, and this is what came out, this ugly thing right here. And so to find the electrical potential, we need to isolate C. And so we have right here, we have V equals V of Y plus C. And what we need to do is we need to plug in 2L, D equals 2L. And so we plug that in for every D and set V equal to 0. So this is what we get right here. This is equally as ugly as that one. And we try to solve for C, we try to plug that in, but it didn't give us, it gave us a very sloppy answer. So every point above, every electrical point for any point above the strip is going to be off of this equation right here, plus C. And that's our electrical potential.
Some sense making on what Jesse just completed. So on our given linear charge density equation, we're given sigma naught times y over L. So another way to tell where your electric field is positive or negative, or when it's 0, or where everything is going, is you could plug in different points for y. So if you did like a positive y value, you'd get a positive divided by L times sigma naught, so you get positive. If you did 0, 0 over a fraction is 0, so you'd get 0. If you did negative, you'd get a negative value. And that makes sense because, I mean, negative, 0, positive. Another way is if you were to look at the magnitude and the vectors of the problem, the closer you are to get into these positive charges, it would want to push you out more, so you would go up. And the further away you get, so it would be stronger, and weaker, and weaker, and weaker. And then down here, the closer you get to the negative charges, it would want to push up as well. And it's the same thing. The further you get, the weaker it would be. And then finally, another graph you could kind of take a look at is if this is the positive y, so kind of flipped. When it's negative, you go up, and this is the whole length of the strip. When it's negative, it goes up and up, hits 0, you hit positive, and you keep going up. To do a unit check, our integral from the previous problem was pretty gnarly, so we went to the wormhole and got it simplified. And this checks out to be, we have Newton meters over coulombs equals Newton meters squared over coulombs times coulombs over meters squared times meters times no units. It's a unitless value. So then we get Newton meters over coulombs equals Newton meters over coulombs times meters. So our final answer is Newton meters over coulombs, which is what the electric field should be in. Another unit check for our electric potential. So we know that electric potential should be Newton meters over coulombs. So K is a constant, which is given as Newton meters squared over Coulomb squared. We have a negative value. Sigma naught is coulombs over meters squared. So if you multiply these together, meter squared, and then coulombs cancels one of the coulombs. So you end up with this on that side. And then here we have, this is in meter, or in units of meters, unitless. This should be down here, but this is meters over meters, so that cancels. Then up here, this is unitless. Log is D is meters. Then we have meters plus meters divided by meters minus meters, so those cancel. So then you're left with meters divided by meters, so you get those cancel. So So then you multiply these, the meters times newtons over coulombs, and you get newton meters over coulombs. For the reflection part, we have two examples that are kind of similar and different. One that's kind of similar is activity 1 in homework 3. We have 3 wires, wire A, B, and C. A and B have certain charge density values, while C has a uniformly charged density. The similarity is wire C compared to our strip are the exact same. The differences are, 1, there's not 3 wires, and 2, like I said, it's uniformly charged, so that doesn't relate to A or B. Another one that's similar is in exercise 2, potential calculations, it's called. We have to find the electric potential at a certain point. So I think it looked something like this. We had to find the charge from here to point A. The similarity is that it's above the y-axis, so it's positive. Just like the homework question, we're also told to find the charge above in the positive y-axis. The difference from this one is we're told a specific point to find. So for our R value, we could have done R is equal to A. In our problem, we're told to find points from where y is greater than 0. So that's not a specific point.